find the area between two functions. So one function is easy, we know what this looks like. This one creates a little problem now, doesn't it? Do you even know what this thing looks like? And you have to have at least an approximate idea of what this thing looks like. Does it look like this? Okay, we have to know this much, okay? And the other one is easy. The other one looks like this, right? First thing first, well then, we need to find the intersection of these 2 points. Because when we say integral, limits of integration is the x values of this. You know what I'm saying? So how do we find the intersection of these 2? Well, do you remember systems of nonlinear functions last year? Yeah, that hideous chart. Yeah, that's why. Okay, this one will just use substitution. Okay, so we have y squared, so we'll have x squared minus 2x plus 1 is equal to 2x plus 6a. So x squared minus 4x minus 5 is equal to 0a. That factors nicely, x plus 1 and x minus 5 is equal to 0. Therefore, x is equal to -1 or x is equal to 5a. Now we have to find the corresponding y values, and that, of course, we'll use this one. So y is equal to -2 or y is equal to 4. These 2. Perfectly good, no problem, nice review. Yeah, everything happens for a reason. So this coordinate right here is -1, -2, and this one here is 5 and 4. Now we can just use this picture. You don't have to put the picture that I'm about to put on your notes, but I want to be precise and I wanted you to see it. This is it, right? Okay, so now you know how to find the intersections. Let me copy this. Okay, now we come back here. I'm going to paste it right there. Okay, now how are we going to find the area between these 2 now? Whenever you talk to not so intelligent individual, they love to give 1-word answer or 2-word answer, simple ones, right? They say, oh, by integrating. Of course, this is by integrating. What do you think? This is calculus, right? It's like, that doesn't really answer the question now, does it? Right? How are you going to integrate? How are you going to set up your integral was my question. It's like 1-word answer. Don't you love them? It's frustrating. See, if we integrate this function, let me write down what that function is. This function is y is equal to square root of 2x plus 6, right? Because y squared was 2x plus 6. Well, what happened to plus or minus? Well, minus 1 is down here. I'm going to write it here. Y is equal to negative square root of 2x plus 6. You know what I'm saying? So when we have plus or minus, plus means this upper half, minus means this lower half. And then in order to distinguish the 2, I'm going to call this one y1 and call this one y2. How about that? Well, if I integrate y1 from this point, which is -3, all the way to 5, it gives me the area of that thingy, which is like, we want the area in between. Let me introduce this function, which I'm going to call y3, and that is x minus 1. So let's just set up this part. This is easier part. I'm going to draw the rectangle. And I want you to always draw the rectangle like I do here. It's very good practice. Okay. Now this width is infinitesimal delta x dx. What is the height of this rectangle? Do you agree that this is y1 minus y2? I mean y3? the distance formula concept? Because we have a same x coordinate, but you have two different y coordinates. You know what I'm saying? So this upper one minus lower one, because the upper one is bigger one, in order to make the area positive. Good. Say yes. So this A is equal to, well, I'm going to call this thing dA, one tiny rectangle, space, don't write, I'm leaving a space for a reason, is equal to y1 minus y3 dx. Good. Okay, well, that's nice, right? Let's figure out what this is. Y1 is square root of 2x plus x minus y3 is x minus 1a. So we can integrate this. Okay, great. Let's integrate. So your a is equal to, from, now here's our problem. What to what? You might say this is negative 3 to 5, right? But is it really? Well, why don't I draw the triangle on that side and see if it works out? I'm a triangle. Did I say triangle? Oh my God, I mean rectangle. You see the problem with this one? It goes outside of our area that we want, because this is y1 function and this is y3 function now, isn't it? No, so that fails in spectacular fashion. Now what do we do? You see, by integrating, that doesn't really answer the question now, does it? So instead, over here, it requires this. Let me adjust this rectangle. I'm gonna end it right there and change the color on it. Right? So this is dx, and then this height happens to be now y1 minus y2, isn't it? Oh, that y2 looks weird. You get it? This function minus this lower half function, which is what I call y2. So you have three different functions floating around. So top part is smooth. This is y1 throughout our region. But the bottom part, your function changes on you. So there's no way to set this up with one nice smooth integral. You get it? So this technique is called partitioning. I'm going to throw the vertical partition right there. You have to cut it right there. So this side is A1 and that side is A2. You get it? So we have to do this separately. So A1, so we'll call it dA1. Here is now y1 minus y2 times dx. Good. Now let's substitute. So that becomes y1 square root of 2x plus x minus negative square root of 2x plus 6a. Which gives you, well, now, A1. Last night I made roast beef for dinner. I got into cooking, mainly roasting, during this pandemic because I'm bored out of my mind. During Christmas, actually, I made prime rib, and it was beautiful. It's spectacular. Last night, I didn't really use prime rib, but but still, roasting is the same idea. And okay, so in roast beef, what is the most important ingredient? This is not a trick question.
Salt?
No, we have something a lot more important than salt.
Beef?
Meat, of course, right? Beef is the thing. Okay, I have nothing against vegetable. I love vegetable as long as it's accompanying meat. Right, so when I prepare this roast beef, first, to me it starts like 48 hours before actually putting into the oven. try it out, and then do you guys know what rub is? This is actually related to calculus, very important. Rub is literally that thingy that you rub it on the meat. To me, it is Himalayan pink salt, not any other salt, but good quality salt makes a big difference in meat. Himalayan salt, pepper, fresh ground pepper. I do have a grinder, so fresh ground pepper, not the one that comes out of a can. And garlic. Fresh garlic is better, but Costco has a really good garlic powder. And then others like paprika, thyme, and parsley. These other ingredients, it's like whatever I have, but those three, salt, pepper, and garlic, those are the main thing. Mix it up, give a good rub, plenty, and then let it sit in the fridge for 48 hours for that salt to absorb to the middle, and then it dries the surface a little bit. Now, yesterday during Panther time, because I'm teaching from home, now I cover it up with butter. Butter makes everything so much better. Butter. And then, while the oven is preheating, I chop onions and apple and a few other vegetables and put it at the bottom of it. Instead of a rack, roasting rack, I use vegetable. That makes a great roast and great vegetable, by the way. See, I love vegetable as long as it's sitting under meat. Now I shove it into the oven. Now, see, this is the meat. This is the most important ingredient in integral. This is called the integrand. I prepare that first separately. Once that is ready and sitting on my counter, this is the vegetable part. Limits of integration. You know what I'm saying? This thingy right here with dx, this is the roasting pan. And vegetable will range from -3, and I'm going to assume you know how to find the vertex. -3 all the way up to that partition, which is -1. You get it? Then I put this meat on top of it. Did that make sense to you? Good. Now, people who are bad at cooking, they tend to just dump everything into the gigantic pot, meat, vegetable together, pour water and start boiling and stirring, right? That's prison food, okay? You're supposed to prepare ingredients separately. That's the key to good cooking, right? So do this integrand first. Some people tend to just try to simplify everything inside the integral, and they usually drop dx and like forget these things. I will never forget to deduct points, okay? So if you know what's good for you, you will figure out this integrand, most important one, separately. Then figure out the limits of integration. Then shove the whole thing into the oven. You get it? I need more room, so I'm gonna bring this guy down about there and resize it while I'm at it. Now, this is a nice use of, isn't it? Especially if I change this thing to this setting, this looks even better, right? Now, here's a little technique of doing use of in your head, okay? All you have to do is imagine this part. Your u is equal to 2x plus 6, so this will be u to the 1/2 power, and du is equal to 2 dx, isn't it? That dx, that x looks weird. Now, this, you just imagine this much, okay? Now, then don't write this next part. So what this will turn out to be is, this is u, and then 2 dx is du. How convenient, eh? So this will turn out to be u, I'm gonna write u for now, u 3/2 and 2/3 power, correct? But we just imagine that much, don't really write it. Watch this. So we have 2x plus 6, 3/2, therefore 2/3 power, but we still have to have that du part, 1/2. So just stick 1/2 here. Actually, I don't even need it because I have that too. So that cancels out. And this evaluates from -3 to -1. How about that? You see how convenient that was? Okay, now here's the most challenging part in AP Calculus BC. You plug it in, multiply and add. Whoa! Okay, who can do this? Okay, fine, you may use a calculator. Oh, come on, don't look at each other and say, oh, somebody please do it. Like, just do it. You'll have to do this on the test, so do it. Otherwise, this awkward silent, uncomfortable moment will continue. So just.
Oh, is it like 16 over 3?
Yes. See, that wasn't so bad, right? I know it's so sad that AP Calculus BC students struggle with this part the most. If I were you, I would just go this far on an FRQ and move on to roast some bigger meat. Because this is a minimal amount of point from here to here, and there's no partial, so either you got it or you haven't, right? That's a minimal amount of point. You with me? Okay, now let's do this second half. Okay, this I'm gonna call A2. Okay, so we already kind of prepared the meat for it. Right, this function minus this function. Limits of integration is from -1. So, oh, that 5 was the 5. -1 to 5, eh? From this partition to where the x value ends in our region. Good. And I'm going to have 2x plus 6 to the 1/2 power minus x plus 1. With me? Now let's put this skill that we just learned to the test, because that thing is still sitting up there, same u substitution. We just imagine that part. And what we have is 2x plus 6, 3/2, therefore 2/3. And now we don't have that 2, so we have to divide by 2, right? Just write that. And then, of course, this cancels. You know what I'm saying? You see how convenient that is? Just write it and cancel it. You don't have to imagine the whole thing. And then minus x squared, therefore 1/2, plus x. And from -1 to 5. Here we go again, the difficult part. What is this one? Somebody punch the calculator and tell me what that is. Oh, come on, people. We haven't got all day. Dang, huh? Be brave, say it with. Huh?
38 over 3.
Yes. See, that wasn't so bad now, was it? Okay, now then, our total area, which I'm going to do here, is equal to A1 plus A2A. Ooh, fraction addition. Tell me you can add this fraction. That, can you do it in your head?
18.
18 is correct. How about that? Wow, that number is nice and round 18. Huh? That was a lot of work, right? Because the geometry of the shape, we cannot draw the one smooth rectangle, so we have to partition it and this and that. There's an infinitely better way than this. Okay, and I'm gonna show you that better way. Okay, that was a nice warm-up round to understand what's going on. Better way is this. Find the inverse function. Isn't that so much better? Yeah, huh? Okay, I'm gonna copy this to your notes. And then we'll compare the two. Let me paste that thing. Whoa, this is big. Okay, this is infinitely nicer setup because if I draw the rectangle, let's throw it right about there, like that. Make that blue. So this thickness, the width is dx. Why don't I call this function y1, which is 1/2 x squared minus 3. I'm assuming you know how to find the inverse functions here. Do you want me to review that with the switch x and y and so? Okay. And this is y2, let me call it x plus 1a. So if I do that, then isn't it just nicely y2 minus y1? And then look, I can draw that rectangle everywhere from this end all the way there, eh? So we don't need to partition this thing, eh? Yeah, that's so much better. So we can do this with one shot, dA. dA here, of course, here is y2 minus y1 times dx, eh? Right, this side times this side. And let's substitute. So y2 is, once again, preparing the meat first ingredient, integrand. So we have x plus 1 minus, and then 1/2 x squared minus 3a. You with me? Okay, let's simplify that even further. Ascending order, ascending order. So we have 4 plus x minus 1/2 x squared. How about that? That's nice preparation, isn't it? Now we lay out the vegetable. Now what you have to be careful here is we have found the inverse function, which means x and y switches, -2 to 1. And this thing goes up to 4 to 5. You know what I'm saying? So you have to be careful. Let me put this in red. It's not from -1 to 5 anymore, right? That you have to be careful with. Good. Now we laid out the vegetable, so we lay the meat down. 4 plus x minus 1/2 x squared. Well, this is very straightforward now. So we will have 4x plus x squared, therefore 1/2 minus x cubed, 1/3 with this, therefore 1/6. And from -2 to 4. Oh, here we go again. Somebody brave. Come through. What is this thing? Multiply and add. Oh, come on. This is 18, of course, right? Which is, how do you like this thing compared to those two? You know what I'm saying? This is so much better now, isn't it? Yeah. Would you believe if I told you there's even better way than this? What? Like, why didn't you start with that then? Well, I do this so that you will appreciate the best way, okay? And I want you to do your homework exactly this way I'm about to show you, okay? I'm gonna go back up and recycle this picture. So let me copy that and come out here and paste it here, okay? We go back to this picture. What we are going to do here is throw this rectangle. Watch this. Horizontally. Let me use red color this time. What? So this width is dy now. You get it? Oh, we need two different functions. This one I'm going to call x1. This is 1/2 y squared minus 3. So we are still finding, in a way, inverse functions, but we are not rotating the picture around. We just use the same picture. X is a function of y. And this one, x2, is, of course, y plus 1. You get it? So this this width, I mean the length, happens to be x2 minus x1. How about that? So my dA now is x2 minus x1 dy. Okay, now whenever I find this dA, it's x times y or y times x. We have to have both variables. You know what I'm saying? Because it's geometry, length, width. You get it? X and y length. And then we replace these things with our given functions. So if this is y, this is our independent variable, this thing matters a lot. We convert, in this case, both of them to y. So we have that equals sign. We have y plus 1 minus 1/2 y squared minus 3 dy. You get it? Now, somebody in calculus BC asked this question before in years ago, so I have to mention this. How do you know which one goes first? Is it this one minus this one, or is it this one minus that one? Like, okay, children, on a number line, this is a greater side and this is a smaller side. Numbers increase if you move to the right. So this is right side minus left-hand side in order to make the area positive. You get it? I can't believe I'm mentioning this, but I have to, otherwise I will get that question. How do you know when to? Okay, calm down, calm down, calm down. So this thing, we have done this before. 4 plus y minus 1/2 y squared. Exactly same thing we had here. You get it? So it'll turn out to be exactly the same way. We just recycle our work. So now our A is limits of integration. Now, let's be careful. Intersection here is back to -1, -2. And 1 over there is 5, 4, right? It's our y value. Y is moving from -2 to 4. You get that? This and that. So we still have to do it according to this variable. After all, it has to be exactly the same thing as this thingy. You know what I'm saying? We are just leaving the picture the way it is, conveniently, but it's the exact same work. Okay, then we have 4 plus y minus 1/2 y squared, and we can pretty much recycle our work. 4y plus 1/2 y squared minus 1/6 y cubed from -2 to 4, and that magically gives us 18. How about that? You get it? Okay. We are still finding the area between the curves, but we're doing it with a calculator this time, as you can see. So suppose we have two functions. F of x is equal to e to the negative x. F of x is e to the negative x, which looks like this. And this is g of x. And that is sine of x. So this first area, these will intersect infinitely many times, okay? So we are pretending we cannot even see this, but this is a calculator problem. So I have my function set up in my TI-84. So let's just put it into the standard window to size up the functions. Okay, this is exponential function. And this is sine function. So that tiny little area right there. Let's try to zoom in to that section right there, shall we? So window, and then x could start from 0 and go up to 2 pi, about 7-ish, right? More than 2 pi. Well, no. About 4-ish, because this is pi right here. So 3 point something, right? Okay, that'll do. And then y value 0 to 1, because the height of the sine function is 1, will do it, but I'm gonna start with a negative 0.2 so I can see the x-axis clearly. You don't have to, and then to 1. Okay, let's regraph, and then this thing shows up nicely. I want to find that area right here. Okay, so first thing we have to do is find the intersections, correct? Because that becomes the limits of integrations. So second, calculate. Of course, intersect, we have all done this before. So first curve, yes. Second curve, yes. Guess, scroll all the way, because it tends to move towards the closer one right there. And then this is it. Now this is what I'm going. Oops. This is what I'm going to call A here. I'm gonna use blue color. This is A. Now, even if I write this down, this will still be, number one, a lot of writing. And if I integrate it after rounding this to the 6 decimal places, that might give me some kind of error. So we have to learn how to store these values into the calculator itself. Okay, so let's do that. Quit. If you press X and store, and I'm going to put it into the letter A, see whatever in previous calculation X value is stored in X. And of course, Y value, Y coordinate is stored in letter Y. But you don't want to use X as the limits of integration, because whenever the calculator does something to this, these are variables, it'll change on you. So you want to restore it into constant A. Now, likewise, let's find the other intersection. So right there, that one. Okay, so second, calculate, and intersect. Okay, first curve, yes, and second curve, yes. And in case you didn't know before, instead of scrolling all the way there, you can actually use the keypad to take a guess. How about that, huh? And this X value, now I'm going to quit and store into my variable, my constant B. How about that? Okay, let me write that down. So this right there is my B, which is approximately equal to 3.096364. Okay. Now, the machine will remember forever. This A is this number. Oh, I did not write A down. So 0.500533. So machine will remember these two. Okay. Now I'm going to draw a rectangle as before. So my rectangle will, let's put it about there, extend down there. Okay, so I need to calculate that dA. Now here, yesterday I called it y1 and y2. Today I'll call it g of x minus f of x. How about that? And that width is still dx. So what I have is g of x minus f of x and then dx. How about that? Now, to set up the integral, then my a is integral from a to b. A being 0.5-ish and b being 3.1-ish. But don't bother writing these, because as long as you specify what a and b are once in the problem, you can still use a and b. Those of you in computer science, this is same as a variable constant declaration. And likewise here, don't bother substituting sine x and e to the negative x. You just keep this like this. This is perfectly good way to present your work. Now at that point, we just punch the calculator. Don't even bother, God no. Don't ever hand evaluate this integral. I know you know how to do it, but there's no extra point for doing such a thing. In motorcycle racing, we ride a motorcycle. It's still faster. So we go over here, math, 9, the hotkey, and there from your letter A to letter B, And then, do you remember how to put these two? This f was y1 and g was y2 in our case, so second, and there is your y2 minus, and then alpha and trace, and that's y1 and the x. Bang. Huh, how about that? So this area happens to be 1.320806. We have to calculate the area between these two functions, right? And first question is, how do you calculate the intersection? Well, the typical way is you feel it. If you plug in 1 here, this whole thing becomes 0, and if you plug in 1 here, that thing becomes 0. So this is an intersection. We cannot really setting it equal to each other and solve it. Either that, or you have to rely on your graphic calculator. And then, of course, if you plug in 0, they both give you 1. So this is it. And second question is, which is higher? Which is above and which is below? That makes a big difference, right? That's what this calculation is. I plug in 1/2 here and 1/2 here, and then this is bigger. You know what I'm saying? You might have to convert this to decimal to figure it out, but wait, not this is bigger. You know what I'm saying? This is approximately, square root 2 is 1.414 divided by 2.707. So this f is bigger. You know what I'm saying? Okay, so that's a preliminary work. Now, having said that, then my dA here is then this bigger one, f of x minus g of x times dx, isn't it? Good. Okay, then plug it in. So we have cosine of pi over 2x minus 1 minus x squared dx. Okay, so we can integrate. Okay, so using the symmetry again, because there's another half on the other side. So from 0 to 1 and then multiply by 2. Good. Of cosine pi over 2x minus 1 plus x squared dx. Good. And then integrate. So this is sine pi over 2x. Is there a minus sign? No, there isn't, right? The quick way is you differentiate this, no minus sign, but chain rule gives you pi over 2. So backward, reverse chain rule. So 2 over pi. How about that? You got this? And then minus x and this plus x cubed, therefore 1/3, evaluated from 0 to 1. And of course, here comes the most difficult part, right? And that'll give us 2 times 2/3 minus 2 over pi. How about that? That 2 is here. Good. Okay, moving on, 33. So these are the functions. X is equal to tangent y, looks like this, and then x is equal to negative, so it's like this, right? So the geometry dictates it's so much easier if we draw the rectangle sideways. You know what I'm saying? Otherwise, I don't think I want to find the inverse function of this. So many reasons to draw it sideways, right? So calling this x1 and this x2, this length of the rectangle is x2 minus x1 times dy. So my dA here is x2 minus x1 dy. And plugging in this thingy, so it becomes 2. They are same thing, so 2 times tangent squared y dy. How about that? Good. So A is now from 0 to pi over 4, because that thing, it says pi over 4 from the problem, right? And then we double it for the symmetry, that to compensate for this lower half. And we plug in tangent. Ooh, how are you going to integrate this? Like this. You remember this identity? Tangent square is secant square minus 1. And then, what's the antiderivative of secant square? Derivative of something is secant square, and that something is tangent. And this is just y. Oh, that's nice and easy. Good. And pi over 4, tangent pi over 4, of course, is 1. So we have 4. Did I put something? I doubled. Oh, okay, I missed that 2 here, right? That 2 is there. See, this 2, and this 2 is from symmetry. So this should be 4. Cut that mistake. So pi over 4, 1, so I'll say 4 minus, and this is pi over 4 times, so it's pi. How about that? Good? Questions? Then we move on to this most difficult one, okay? And then you guys wanted both A and B? I mean, B and C? Because A part is just sketching, right? Okay, now, so B part is with respect to Y and the other is with respect to X. Okay, I'm gonna have to just sketch both of them anyway, it looks like, in order to explain this. So B part. So this thing, it looks like this. And this right there is 4. Therefore, this is 2. Good. Now we're going to draw a line somewhere here. And that is C. Which means this is square root C, eh? You get that much? We don't have to know this for part B, but eventually. Now I have to integrate this to find, so that this area is equal to that area. You know what I'm saying? Okay, so why don't I draw this rectangle sideways, like they suggest? Like that. Good. Then this is dy, and do you see this entire thing? This much is x right there. So far, so good. So my dA, I'm going to call it dA1, the first part, and this is A2. dA1 is equal to 2x dy. And our function is, of course, is equal to y is equal to x squared. Do you see this function is y is equal to x squared? So x is equal to square root y, isn't it? You know what I'm saying? Say yes. Okay, so A1 happens to be from 0 to C of 2, and then I'm going to write it like this so that it's easier to integrate. And that is y to the 3 over 2, therefore 2/3 with that 2 is 4/3, eh? 0 to C. You with me? So we have 4/3 C to the 3 over 2 power. That 3 does not. Questions? Okay, then A2. We can recycle this work. So A2 will be just from C to 4 of the same integrand, eh? So recycling our work, we'll have 4/3 y to d 3/2 from C to 4. So far with me, if you substitute 4, 2q 8, 32/3 minus, and the other one is same as this. So far with me? Question. And then last thing is, we have to equate the two. Right? And solve. So what we'll have is put it on the other side. So we have 8/3 C 3/2 is equal to 3/32/3. That of course means C to the 3/2 is equal to 32. What? 4. So that tells you C is equal to 4 to the 2/3 power. How about that? Good? Say yes. Okay, part C. I'm gonna I'm gonna draw that same page. Oh, right, this is a computer. I can copy and paste, eh? Beauty. So this is part C. But I need to erase that thingy. Okay, so this time I'm going to draw the rectangle vertically, because that's what they tell me to do. So I have that rectangle. So my dA here is, y2 minus y1, except that's c minus x squared, isn't it? That's simple enough. Good. Now, so what we have to do is A is now use the symmetry, so 0 to square root c, right, from here to here, and then double it. That'll give us this area, A1. You know what I'm saying? A1. And integrating, so we have cx minus x cubed, therefore 1/3, and from 0 to square root c. And that'll be, we have c to the 3/2 power 8, 1/2, minus 1/3 c to the 3/2. Good. Too much algebra here? C, 1/2 power, yeah. And that's 1 minus 1/3, so 2/3 with a 2, we have 4/3. Good. Say yes. And that looks familiar from here, right? The other side is headache, isn't it? From here, oh, and this part creates a partitioning problem. So instead of doing it that way, what I'm going to do is calculate the total area. Total area must be from here to there, you know what I'm saying? So it'll be 4 minus x squared instead of c minus x squared. How about that? So my total area is still doubling it from 0 to, instead of square root c, I go up to 2 now. 4 minus x squared dx, and that is 2 times 4x minus 1/3 x cubed from 0 to 2. That 2 looks weird. And then substituting it, so we have 8 minus 8 over 3a. Say yes. So that is 2/3, so 16 over 3, 32 over 3. Good, which looks familiar too, 32 over 3 up there. Now, finally, you set them equal to each other. Or no, not set them. A1 is equal to 1/2 of A totally. So A1 is 4/3. C, 3 over 2 power is equal to half of this, so 16 over 3. Good. So C to the 3 over 2 power is equal to 4. Too much algebra? No? Is it good enough? So C is equal to 4 to the 2/3 power.